In this video, I'm going to talk about Maxwell's equations, specifically Maxwell's equations in free space. What do we mean by free space? By free space, we mean a vacuum. And a vacuum doesn't have any charges in it. There's no charges and there's no currents. Because what is a current? A current is the movement of charge. Anytime you have a current, that's charge flowing through space, right? It's the time derivative of charge. That's what current is. So what we're going to do is we're going to take these red equations. These are Maxwell's equations. We've got Gauss's law for electric fields, Gauss's law for magnetism. Then we've got Faraday's law of induction, and we've got Ampere's modified law, right? This is the displacement current term, and that's Maxwell's addition to Ampere's law. So these four are Maxwell's equations in general, right? This is the most general form of Maxwell's equations for their differential form, right? This is not in integral form. This is in differential form. And you can see we've got these little del operators. They're sometimes called nabla, this upside down triangle. And here we've got the dot product with the del operator. Here we've got the cross product. When you have the dot product, that's divergence. When you have the cross product, that's curl. So divergence is describing how something emanates from a source or goes into some kind of sink. And curl is talking about rotation or some kind of circulation in a vector field. Now this E represents the electric field, and this B represents the magnetic field. What about these guys on the right-hand side? We can still see B and E appearing. We also have J, which is the current density vector. That's how much current is going through a little patch of area, a tiny little infinitesimal patch of area. That's what this is. And it's also got a directionality associated with it. And that directionality is defined by the direction of movement of the positive charges. So if you take the surface integral of this guy, you're actually going to get the current. So this is analogous to current. This term is talking about the flow of current. These guys are changes in the electric and magnetic fields with respect to time, right? These partial derivatives with respect to time. And this over here in the top, we've got rho. That is the charge density, right? It's not the mass density, it's the charge density. It's the charge per unit volume at every point in space. But what we want to do is we want to take these general differential equations and we want to turn them into the specific case of a vacuum, right? What are Maxwell's equations doing when it's a vacuum, when there's no charges and there's no currents? So first of all, which of these are going to remain unchanged? Which of these are valid in a vacuum as well as in general? Well, we can look at this second equation over here, Gauss's law for magnetism. It says that the divergence of the magnetic field is zero. This is saying that there's no magnetic monopoles. And that's going to be valid regardless of where you are. Unless, of course, we discover magnetic monopoles. But that's for another video. So this is always going to be valid. So we can put a tick next to that. That's always going to be valid. So we don't have to modify this when we're in a vacuum. What about this one over here, the curl of the electric field? Well, there's no charge and there's no current in this equation over here. So if there's no charge and there's no current, we don't have to make any modifications. There can still be electric fields, there can still be magnetic fields when you're in a vacuum. So that's fine. So this is also fine. But what about the first one, Gauss's law for electric fields, and the last one, Ampere's modified law? What about these two? We're going to have to make some modifications. So let's have a look at this one because it's simpler. Let's have a look at that one first. So the divergence of the electric field is proportional to how much charge density there is in a region of space. So what about in a vacuum? What's the charge density in a vacuum? Well, it's actually zero. So we can say rho is zero. And it's actually zero for all of the x, y, and z coordinates if you're in a vacuum. That's what free space means. You're in a vacuum and there's no charges, right? And if rho is equal to zero, that implies that the divergence of the electric field is also equal to zero, right? Because the divergence is only due to this charge density. If there's no charge density, there's no charge there, then there's not going to be any divergence. So divergence of the electric field has to be zero. So there's not going to be any sources or sinks for the electric field, right? Positive charges would be sources where the electric field is emanating, and negative charges would be kind of like sinks where electric field lines go in and they finish, they terminate at the negative charge. So they originate at positive charges and terminate at negative charges. But if there's no charges, then there's no divergence at all. So that's the condition of rho equal to 0. So if the charge density is equal to 0, then the divergence of the electric field is equal to 0. So we've modified this. So now we have 3 of Maxwell's equations, and they work in a vacuum. What about this last one? What about Ampere's modified law? So what are we going to have to change? Well, there can still be changing electric fields in a vacuum, so this term has to stay. There can still be curl in a magnetic field, right? This B field, there can be a B field, and there can be an electric field in a vacuum. So both of these terms have to stay. But what about this term over here? What about the current density vector? Well, if we don't have any charge, as we said before, if you don't have charge, then you don't have a flow of charge either, right? You can't have a flow of charge if you don't have any charge to begin with. So that means that this term is going to disappear. So I'll write this over here. J, this vector, is going to be 0. There's not going to be any flow of charge, and that's what this guy is telling us. It's the electric current vector, and it's telling us the electric current density. So this is actually going to be 0 for a vacuum. So now what we can do is we can eliminate this term, and that implies that the curl of the magnetic field is just equal to mu naught times epsilon naught, these little zeros, times the partial derivative of the electric field with respect to time. And now you can see there's a little bit of symmetry between the curl of the electric field and the curl of the magnetic field. It's not a perfect symmetry because we got a negative sign here and we got some constants out the front, but we can tell that a circulating electric field is due to a changing magnetic field, and a circulating magnetic field is due to a changing electric field. So electric fields can cause magnetic fields to circulate, and specifically changing electric fields can cause magnetic fields to circulate, and vice versa. Both of these guys can cause each other to circulate. As long as there's a change in the electric field or a change in the magnetic field, there's going to be circulation in the other one. But what about divergence? Divergence is 0 for both the electric and the magnetic field. This is only valid in a vacuum. So a vacuum is a special case where there's no charges and thus there's no currents, right? And if there's no currents, this vector is going to go to 0, right? So this is the same as saying the current is equal to 0. And this guy can actually be written as the surface integral of J, right? The current is the surface integral of this guy. And the charge is the volume integral of this guy. So this is actually equivalent to saying, well, Q is equal to 0, where Q is an enclosed charge, right? So the total charge that is there. So Q, the charge, is always going to be 0, and if there's no charge, there's no flowing charge, so this condition is satisfied. Now what do we have? We have Maxwell's equations in free space, right? We have, first, Gauss's law has been modified. Now it's saying that the divergence of the electric field is 0. Then we have Gauss's law for magnetism. It's consistent. Again, it hasn't been changed at all. Then we have Faraday's law of induction. It's staying the same because there's no charges appearing in this term. And there's no currents either. Then we had Ampere's law, and that's been modified a little bit. We had to drop this term, but there still could be a changing electric field, so this term remains. So the curl of both the electric and the magnetic field don't necessarily have to be 0, but the divergence of the electric and magnetic field, they have to be 0 when you're in a vacuum. So this was Maxwell's equations in free space. That's when you have no charges. This is very useful, especially when you're deriving the wave equation, which we will do in another video in this playlist.